Welcome back, students. This is the second set of lectures for Unit 13, Kinetics. And we're going to start this time by talking about rate laws. The rate law expresses the relationship of the rate of a reaction to the rate constant and to the concentrations of the reactants raised to some powers. For a reaction of the form that we see here, once more, the uppercase letters represents formulas of reactants, A and B, products, C and D, and the lowercase letters A, B, C, D would represent the coefficients of the balanced equation. This is what the rate law looks like. Notice the rate equals K times the molarity of A to some power X times the molarity of B to some power Y. Notice, it's not the stoichiometric coefficients. X and Y may or may not be the same as the stoichiometric coefficients. Okay, so let's see what these things are. K is the rate constant. And when we look at the rate in terms of A, we say that the reaction is of the xth order in A. Why? Because that is the power that we have, the exponent we have with the molarity of A. We could also say that the reaction is of the yth order in B, because that is the exponent that we have for the molarity of B. Now we can also talk about the overall reaction rate law, and we could say that this reaction is of an order x plus y overall. So let's say that x were equal to 1 and y were equal to 2, then we would say this reaction is first order in A, second order in B, and 1 plus 2 third order overall. Okay, now this is very important. Note that the rate law is expressed only in terms of the reactants, and the rate that is calculated always is positive. So let's look at how we would apply this idea here. Let's look at this reaction here of fluorine with chlorine dioxide to produce a kind of complicated molecule, FClO2. All of this is in the gas phase. Let's say that a scientist was able to perform an experiment measuring the rate of this reaction. Now here's one of the problems we mentioned earlier on. If we simply measure the change in the molarity of, say, a reactant over time, right? We take this data here. One of the things that's going to happen is, again, that it is a curve. So it's very difficult to get very good assessments. So if we look at the beginning part of the reaction, right, you can see that it is fairly linear in that initial stage. As we're going to see in future chapters, several things happen as time goes on. One of them is it is more difficult for the reactant to find other reactant molecules to react with. Also, many chemical reactions, as we will see in the future, are reversible, which means that as the products begin to form and accumulate, the reverse reaction begins to happen. That is why taking advantage of this near linearity of the initial stage of the reaction, we typically look at what we call the initial rate, and that is what you can see here in this table. They have measured the initial rate at different initial concentrations of each one of the two reactants. Now this is what the rate law will look like. And our goal then is to try to find what are the values of x and y. So let's go to our document camera and let's start out by doing a kind of like a simple approach to this, just purely mathematical, and then we'll come back here to the PowerPoint. Okay, students, let's try this practice. Notice that the data set that we're giving here, the data table we're giving here has like 3 sets of experiments. Each one lists the concentration of each reactant, and then the initial rate measured. We're not told what the method was, but it doesn't matter at this point. So what's the strategy? The strategy consists of picking two data sets where one reactant is kept at the same molarity and the other reactant is changed by a convenient multiple. Remember, the rate law should apply for any one of these experiments. So for this one here, I've highlighted experiment 1 and experiment 3. So let's look at what is the ratio between those two data sets. So we're going to start out by saying that rate 3 over rate 1, all right? And we're going to say that that is essentially following the rate equation here. So rate 3 would be K times the concentration of fluorine for experiment 3, which is 0.20, and that should be to the X power. And then we have the concentration of ClO2, which for experiment 3 is 0.010. We're not going to put the molarities and the units here. We're not going to bother with that because they're actually all going to cancel out. All right? And it's to the yth power. Now, for the first set, the rate should be equal also to the same constant times whatever the molarity of fluorine is, which in this case is 0.10 to the X power, times the concentration of ClO2, which in this case we kept the same. You'll see why mathematically in a moment. Okay, so let's look at what are the rates for these two experiments. For experiment 3, it says here 2.4 times 10 to the negative 3. All right. And for experiment 1, it was 1.2 times 10 to the minus 3. Notice that in the actual rate law, several items are going to cancel out. K is the same, so it cancels out. And since the molarity of ClO2 is the same, doesn't matter what Y is, this is going to cancel out. So we're going to end up with this being 0.20 to the X and 0.10 to the X. Okay, so on the on the left, the ratio of the rates. In this particular set, it's pretty straightforward. This is 2. Don't worry about the sig fix at this point. Okay, if you want to worry about it, let's go ahead and do it, 2.0. Okay. And remember, when you have two items in a ratio, which each of which is elevated to the same power, that's the same thing as putting the ratio, all of it, elevated to that power, which then gives us, again, 2. Okay, if you want to be kind of like a little, like fidgety about sig figs, we're going to leave it like that. You don't have to do that because we're trying to look for essentially an exponent, which is typically going to be a single digit figure. So I think that in your head you can tell what power do I elevate to in order to get 2. Well, that tells me that X equals 1. So this is the standard strategy. Again, you're going to be given a table with concentrations and rates, and you'll have to pick sets of 2 in which one reactant is kept constant and the other one is changed, usually by a convenient multiple. You double or triple the concentration, and then you measure the initial rates and you calculate what are the ratios and you solve for the value of X. Now, you can do the same thing on your own. I want you to go ahead and do the same thing for your own to solve for Y. Now, in that case, which two sets of data do you think you should use? Right. You would use experiments 1 and 2, right? Use experiments 1 and 2 to solve for y. Okay, let's go back to our PowerPoint presentation now. Okay, so now we are familiar with the general strategy that is carried out in doing these things. Now, I showed you the long form of doing this analysis because unlike the types of problems you typically get in textbooks and in little presentations like this one, real world data never fits as perfectly as shown in these examples. And you're going to be doing an experiment where you're going to be measuring out the rate of a reaction and doing this same table and this same type of analysis. And you'll notice that when you do things, by hand, the numbers might not come out as clean. However, many times when you look at data that is given to you, many times the numbers just jump out at you and you can actually shortcut your way to the solution. For example, in this case, where we compared reaction set 1 and reaction set 3, we can see that while maintaining ClO2 concentration constant, if we double the concentration of fluorine with chlorine dioxide constant, the rate doubles. So that means that doubling one reactant causes the rate to also double, meaning that they have essentially a first order relationship. And so you can shortcut your way to saying, yeah, x must equal 1. In the other case, let's say we compare reaction sets 1 and 2. You can see here that if you quadruple the chlorine dioxide concentration while maintaining the fluorine concentration constant, the initial rate also quadruples, which means that here also the exponent y must be equal to 1. So once more, notice that although I showed you a long form official way of doing these calculations, sometimes with data they give you which is a little more sanitized, you can take a shortcut to the solution. So we know now that the rate law for this reaction is K times fluorine concentration times ClO2 concentration. In other words, the reaction is first order with respect to fluorine, first order with respect to chlorine dioxide, second order overall. Now, many times you are asked to find the value of K. As we will see later in this unit, the value of K is dependent on the temperature. And it's not clear here that they gave us the temperature at which this was done. Normally, in the absence of that information, typically you assume that this is at 25 degrees, but we don't know. So we're going to leave it at that. But if push came to shove, you could take any one of these sets of data, plug in the value of fluorine, the value of chlorine dioxide, the value of the rate, and you could solve for the value of K. But I want to save that for some more detailed analysis later on. All right? So again, feel free to stop the video at any time when you have anything that's not clear. So you can go back over it or perform the calculations yourselves and make sure that you understand what we are doing, okay? Okay, so a few observations that we need to make about rate laws, all right? Remember that a rate law is always determined experimentally. You cannot look at a chemical equation, even if it's balanced, and derive the rate law from the chemical equation. You must derive the rate law experimentally. Remember that the reaction order is always defined in terms of reactant, not product concentrations. Because as we saw, only the reactants are included in the rate law expression. as opposed to the general rate expressions that we talked about in our first lecture. Number 3, the order of a reactant is not related to the stoichiometric coefficient of the reactant in the balanced chemical equation. So let's look at this reaction that we were studying. Notice that experimentally, in other words, from the data they gave us, we determined that the reaction is first order in fluorine and first order in ClO2. However, you look at the coefficient in the equation and it is 2 for chlorine dioxide. And again, although it is implicit, we don't write the exponent 1, we know that the exponent that would go in here is 1. Therefore, you can see that the order with respect to that reactant is not equal, it's not related to the stoichiometric coefficient in the balanced equation. Okay, I'm gonna let you students work this one out. Here is again a set of data for the following reaction, S2O8, which has different names. Sometimes it's called the peroxydisulfate ion. I've seen other names for it. Reacting with iodide ions to produce a sulfate ion and I3 negative, which is actually called the triiodide ion. It's a very interesting reaction that is used in many, like an accessory to other reactions, as kind of like an internal timer for those. And hopefully I'll get to talk about that when we do that, some of those experiments later on. Anyway, the task here is to determine the rate law and calculate the rate constant, that is the value of the rate constant for the following reaction from this data. Again, they don't give us the temperature. Let us assume that is being done at 25 degrees Celsius, which is what we normally call room temperature. Okay, remember the strategy. Pick 2 sets of data in which one of the reactants has constant concentration and the other one has been varied by a convenient multiple, and compare the ratios of the initial rates to the ratio of the rate law expressions and solve for the exponent of each one. All right, if you want, please pause the video here and work on it and then come back here. Okay, so give you time to do that and then let's come back. Again, we are going to find that the rate law would be written this way, and we've arbitrarily picked the S2O8 ion as the one that has X and the iodide ion as the one that has Y. That is totally arbitrary, don't worry about that. Notice that if we compare experiments 1 and 2, when we double the concentration of iodide, the initial rate also doubles. So that means that there is a direct proportion between the rate and the exponent of iodide, which means Y would equal 1. Now, if we compare experiments 2 and 3, we notice that in experiment 2 and 3, we've kept iodide constant and we have varied the peroxydisulfate ion concentration. And if we compare the rates, we see that as we double the S2O8 ions concentration, the rate also doubles. And once more, that tells us that X equals 1, and therefore we can write the rate law as rate equals K times S2O8 ion times iodide ion, both of them first order, and the overall reaction would be 1 plus 1 second order in this case. Now, the other question was what is the rate constant here? So let's see what that is. We're going to pick any one of these 3 data sets would be fine. So we solve for K and we have rate over the product of the molarities of each reactant to the first order each. So again, like I said, let's pick any one of them. We can pick experiment number 1, for example. and say that the rate was 2.2 times 10 to the negative 4. The concentration of S2O8 was 0.08. Concentration of iodide was 0.034. Now, in this particular instance, it is important that we watch out for the units. Notice that in this case, we're going to be able to cancel one of the molarities here. And I don't know if I can use this little marker here. I'm going to go ahead and try to use it. So you can see where that molarity could cancel with that molarity, which would leave both the seconds and one of the molar units in the bottom of the ratio here. So that means that when we finally calculate all of that, we get 0.08 per molar unit per second, which of course, as we said before, we could write as molar units to the negative 1 times seconds to the negative 1. Please keep that in mind as we go into the next section, because when we analyze some specific types of reactions, the units on the rate constant are kind of a giveaway as to what is the order of that reaction. Okay, so we're gonna pause here, and when we come back, we're gonna discuss what we call first order reactions. Thank you very much.